Hello and welcome to this look at a question on ozonolysis, which is not on the A-level specification. So this will be an applied A-level exam question with a focus on constructing an unseen mechanism. It's from the OCR Chemistry A, Synthesis and Analytical Techniques, June 2022 paper. It's question 16c. The question is testing your ability to recall what curly arrows actually mean in terms of electron transfer when bonds are broken and made, and use this to predict an unseen mechanism. And in doing so, predicting what bonds are broken and made during the construction of this mechanism. So it says ozonolysis is used in organic synthesis. Ozone breaks carbon-carbon double bonds to form carbonyl compounds. So essentially, a carbon-carbon double bond breaks and a carbon double bond oxygen forms. So in actual fact, for every single C double bond C that breaks, 2 C double bond O's form. So in the two examples we're being asked to think about, you go to the double bond and you make sure it breaks. So in the top example, the two blue sections form two separate C double bond O based molecules. In the bottom section, the remaining blue section is intact, so only the carbon-carbon double bond part of the ring, which is highlighted in yellow, actually breaks open. So a C double bond O appears on each new end of the carbon chain now formed. So that gives you these structures here. So moving on to the next part. So what I'm going to do here in this part, where they ask you to draw the structure for the product or products of this step, you need to follow the curly arrows and think about what each one means. So if we start on the left-hand side, the curly arrow coming off the O double bond O means the pi bond of the O double bond O will break. So pi bonds are always weaker than sigma bonds, so they always go first. The curly arrow points onto the oxygen that has the positive charge, so that must mean 2 electrons are moving onto that O+. Going down to the methyl butene molecule, the pi bond of the carbon-carbon double bond this time breaks. Again, the pi bond is the weaker of the two parts of the double bond. So 2 electrons will move onto the oxygen atom. So if I just follow the arrow, we're talking about up here. So 2 electrons move onto that oxygen. So you can see a lone pair on the oxygen that's got a negative charge. So that lone pair will move on to the other carbon. So if we take the lone pair here, we're essentially following this lone pair to this carbon atom. So with a little bit of thinking and head scratching, hopefully you can come up with something like this. So what I'm going to do is point at the various parts of that molecule that's formed and link them to sections 1, 2, 3 and 4. So if the pi bond of an O double bond O breaks, which is section 1 in blue, the consequence in purple is that an O single bond O will form instead, which is exactly what you've got there. If you've got an O+ that picks up 2 electrons, that completes its outer shell. So now it's an oxygen atom with no charge. So 2 things happen as a result of the pi bond of the carbon-carbon double bond breaking. Firstly, the carbon-carbon double bond becomes a carbon-carbon single bond, and a new carbon single bond oxygen will form where the 2 electrons went. And finally, the lone pair from the oxygen that's negatively charged moves onto the carbon on the right-hand side of the double bond, and that now becomes a bond pair in a new formed C single bond O. Okay, hopefully this has been a useful look at an unusual mechanism and also a reminder of how you can use simple mechanistic ideas to construct something quite complicated. As always, thanks for listening. Until next time, see you soon.